In the last video, we developed a rate expression for a catalytic reaction that operates close to thermodynamic equilibrium, the ammonia synthesis reaction. So our rate expression was of the form R equals the forward rate of the first step, which was dissociative absorption of nitrogen. So that's K1 pressure of nitrogen times the vacant site coverage squared, minus the reverse rate of that step, which depended on a rate constant and the coverage of absorbed nitrogen atoms squared. This rate equation could be expanded to a form that looks like this, where our vacant site coverage we expressed through a site balance, all in terms of measurable quantities. So each term in this denominator represents the coverage of a different adsorbate, so hydrogen, NH2, NH, N, NH3, and vacant sites, all divided by the coverage of vacant sites. So we can write an equilibrium for the overall reaction, N2 plus 3H2 going to 2 ammonia molecules, and we'll call this equilibrium constant KEQ. So we can express the overall equilibrium constant KEQ as the product of the equilibrium constant for each elementary step raised to its stoichiometric number. So in this case, KEQ is equal to equilibrium constant for step 1, that nitrogen dissociative adsorption, times that of step 2 to the third power, since the stoichiometric number of the second step, the hydrogen dissociative adsorption, was 3. And then all our other steps had a stoichiometric number of 2, so they'll be raised to the second power. So looking back at our rate expression, we can identify this term on the right-hand side of the equation as the overall equilibrium constant for the reaction. So with this in mind, we can rewrite our rate expression as the rate constant K1 times the pressure of nitrogen times the coverage of free site squared times the quantity 1 minus pressure of ammonia squared divided by the pressure of nitrogen times the pressure of hydrogen cubed times 1 over the equilibrium constant for the overall reaction. So furthermore, we can see that this term here is going to be equal to the equilibrium constant when the overall reaction is at equilibrium. So it's simply the partial pressure of products raised to their stoichiometric numbers divided by the partial pressure of reactants raised to their stoichiometric numbers. So when the overall reaction is not at equilibrium, this value is going to be less than KEQ. So the partial pressure of the product ammonia is going to be less than it is at equilibrium. So this term, that's the pressure of ammonia squared divided by the pressure of nitrogen times the pressure of hydrogen cubed times 1 over the equilibrium constant for the overall reaction, is a function that ranges from a value of 0 to 1 and tells us how close the reaction is to equilibrium. We call this term the approach to equilibrium, and we'll denote it gamma. So now using this term, we can rewrite our rate expression. So it's now simply just going to be the forward rate of step 1 times 1 minus gamma, the approach to equilibrium. So we can see that if gamma is 0, the reverse rate is negligible, and the rate is simply given by the forward rate. As gamma gets close to 1, the forward and reverse rates become equal, and so the overall rate goes to 0, as we would expect at equilibrium. So here we've seen how we can develop a rate expression for a reversible reaction in terms of an approach to equilibrium. So the approach to equilibrium will always be the partial pressure of products to their stoichiometric coefficients over the partial pressure of reactants to their stoichiometric coefficients times 1 over the equilibrium constant for the overall reaction. Our overall equilibrium constant, again, we can write as the product of the equilibrium constants for each elementary step raised to their stoichiometric number. So in this case, that would be K1 times K2 cubed times K3 squared, K4 squared, K5 squared, K6 squared. Then finally, the only remaining value in our rate expression that we don't know is the vacant site coverage. So from our site balance, we came up with an expression that wrote the vacant site coverage as a function of partial pressures, so this is measurable quantities, and equilibrium constants.